Of all the theories proposed by astronomers to try and explain the observed features of our universe, none has captured the imagination more than the Big Bang. This model has transformed our understanding of the cosmos and the origins of space and time. And the father of the Big Bang was the Belgian astronomer Georges Lemaitre. Born in 1894 in Charleroi, Belgium, Lemaitre served as an artillery officer in the Belgian army during World War I and subsequently trained as both a priest and a physicist. It was Lemaitre's creative genius and vision that rewrote our understanding of the universe in a single theory that could explain phenomena observed beyond our own Milky Way. Phenomena which, in the early decades of the 20th century, were perplexing those astronomers who were struggling to understand both the scale and the history of the cosmos. For hundreds of years, observers had noticed seemingly cloudy regions of the night sky, nebulae. As the quality of visual, telescopic and photographic data improved, more and more details were resolved. Many of these nebulae seemed to show some type of spiral structure and, as is so often the case in science, two completely opposite explanations emerged as to their nature. To some, these clouds of dust and gas were thought to be relatively small phenomena located within our own Milky Way galaxy, which, at the time, was assumed to be the extent of the whole cosmos. To others, however, the spiral nebulae were island universes, separate, vast collections of billions of stars like our own galaxy, but at enormous distances beyond it. The key to understanding the nature of these nebulae is the technique of spectroscopy, based on the science of atomic physics. Each element has its own unique pattern of spectral lines, its own electromagnetic optical fingerprint. Now, if we compare the light being emitted by a star or a galaxy with reference light produced by different elements here in laboratories on Earth, we can match the patterns of the different features at different wavelengths and determine the chemical composition of objects in space. But the potential of spectroscopy extends beyond just identifying the chemical composition of planets or stars or galaxies. In 1912, spectroscopic measurements of many of the spiral nebulae showed a redshift, a shift in the position of their characteristic spectral features caused by a stretching of their wavelengths. This observation suggested that the spiral nebulae were actually receding from us, getting further away from Earth. And measurements of the amounts of redshift could be used to determine their velocities of recession. As more observations were conducted on other spiral nebulae, further patterns of redshift were observed. It was as if we were located at the centre of an enormous expansion, with the nebulae flying apart in all directions. In parallel, observations of variable stars within the nebulae, coupled with the use of telescopes large enough to resolve individual stars within them, confirmed that they were in fact hundreds or even thousands of times more distant than the stars within the Milky Way, strongly suggesting that they were entirely separate galaxies, other island universes. How could these observations be interpreted? What could be causing all galaxies to be receding from us? Evidence was presented during the great 1920s debates on the nature of these measured redshifts. But it was Lemaître's analysis, coupled with his familiarity with the general relativity theory of Einstein, that led him to a startling conclusion. One which would shatter the generally accepted notion that the universe was in a steady state, forever unchanging on cosmological scales. In 1927, he proposed that the only model which could explain these observations in the light of general relativity was that the entire universe was born from a single origin which he called the primeval atom. An explosive disruption of this origin sent material flying out in all directions, and it was from this material that the galaxies subsequently condensed. This model could explain the measured redshifts. From a single event in the distant past, the entire cosmos was born. In 1929, the American astronomer Edwin Hubble, building on the observations conducted by Vesto Slipher nearly 2 decades earlier, experimentally measured the redshift of nearly 50 galaxies and, plotting the velocities of the galaxies against their distance, discovered a pattern that emerged from the data, just as predicted by Lemaître. The further away the galaxies were, the faster they were receding. But also, the relation between their distances and recession velocities was linear. And the constant of proportionality, now known as Hubble's constant, would, in principle, enable the age of the universe to be determined by simply reciprocating the constant. It would take nearly a decade before Lemaître's ideas were generally accepted by cosmologists. Einstein graciously declared in 1933 that Lemaître's theory was the most beautiful and satisfactory explanation of creation to which I've ever listened. But the renaming of Lemaître's theory as the Big Bang came later still, by the British astronomer Sir Fred Hoyle in a radio interview in 1949. Lemaître's final vindication came 15 years later, with the fortuitous discovery in 1964 by Arno Penzias and Robert Wilson of the cosmic microwave background radiation, in which the entire universe is immersed. This is the final afterglow from the creation of the cosmos, now accepted to have occurred 13.7 billion years ago. This image shows the highest resolution map we currently have of the variations in the cosmic microwave background. It's a record of the time when the universe was only 380,000 years old.